Hello, everyone. Thank you for joining us today. My name is Saurabh Kapoor. I lead product management strategy for Dell Networking. So before we get started on the PTP discussion and how we're bringing this technology into the telco, O-RAN, and 5G use cases, a quick view into how the networking world is evolving over the years, right? So what you see on the screen is basically an evolution journey in the networking side. Like traditionally, we saw that whenever we had to bring in a feature on the networking side, our ecosystems were dependent on the vendors to deliver features, capabilities, and technologies. So over the years, networking has got disaggregated. The hardware and software technologies have got disaggregated. Dell has been championing that initiative since 2014, bringing the choice of network operating systems on the hardware platforms, bringing more choice, flexibility with respect to innovation and technology we want to have on it. And now further accelerating that with Sonic. Sonic stands for Software for Open Networking in the Cloud. It's a brainchild of Microsoft, now part of the Linux Foundation ecosystem. You have every major merchant silicon vendor to ODM and system service provider rallying around this technology, taking it further and extending it. So we started on the Sonic journey around 2017 timeframe, working with Microsoft and Broadcom and partners and taking that into the community forward. It's a great technology, brings container architecture, modularity into the ecosystem, bringing more choice and flexibility. It's based on open standards, truly open from an architecture standpoint, and given that it's supported across a variety of silicon solutions to system and service providers, it allows you that unified fabric of software that runs across a variety of platforms. So Sonic is the future of networking. As I mentioned, it's an open source technology, part of the Linux Foundation ecosystem. A lot of momentum, innovation happening around this. Over the last few years, there's a lot of enablement that has happened into that front. It's deployed across a variety of hyperscalers to enterprises and telcos now. It's based on four main principles, right? The first one is the notion of control, where it gives the users more control on the fabric. The modular architecture, the container architecture of this technology allows you to pick features and capabilities that you need in your operating system. The ability to extend this technology, add features, capabilities in containers makes it more extensible. The agility to add features and do warm reboot, fast reboot, and the likes of those capabilities, runtime without any data plane downtime is very significant. And finally, this being an open source technology, the element around collaboration is significant. There's a lot of momentum happening around Sonic. It's part of the Linux Foundation project, so we have a governing board, championing a lot of adoption and growth of it. The technical steering committee enabling features, capability, and the use cases supported with Sonic, and an outreach committee that is responsible for the adoption and awareness of this technology and what it's capable of. In terms of the market traction, as I mentioned earlier, right, Sonic has been around and it's grown out a lot of places beyond Microsoft as well over the years. We started with Sonic deployment across a lot of L3 underlay use cases. These were tier 2 cloud providers, managed service providers, rolling out Sonic into the production, taking the best practices of Microsoft and other hyperscalers, bringing cloud-inspired architectures into their ecosystem. Then we brought in a lot of features for multi-tenancy into the environments, extending Sonic out to the enterprise market, hardening it, testing it, validating it, making sure it's enterprise from both feature perspective and also delivering on the supportability and the deployment capabilities for it. The last few years, we have spent a lot of time enabling hyper-converged infrastructure, converged infrastructure-related use cases, bringing in the telco Q&Q and VLAN stacking kind of use cases to extend Sonic capabilities out to the telco use cases. And very recently, taking the whole thing into mind around generative AI and the Ethernet's based capabilities, we've started to bring in a lot of capabilities around RDMA, Rocky-like capabilities, and a lot to come on that front to enable generative AI fabrics with Sonic with that enablement. So a lot of momentum around Sonic, great set of initiatives happening in the community. I'll hand it out to Sandeep to walk us through the bunch of use cases we have in production with Sonic.
Thank you, Saurabh. So as far as the main thing for us is to drive disaggregation, and in order to do that, we wanted to make sure that Sonic use cases keeps expanding, right? So when we talk about the various use cases, basic IP underlay fabric is there. You have use cases where you have VXLAN overlays that could start from even the servers or servers directly. So we are just in that particular case underlay network. So we have integration with VMware, their ESXi switch on that side, NSX integration, and then we also have provided various use cases where the if customers want scalable VXLAN overlays, then they can use basically with our devices the very large scale of routing, switching, overlay technologies on the platforms, right? So today we have the all varied set of use cases, including multi-site DCI capabilities that are there, including higher scale of up to 1 million route capabilities, large MAC table capabilities that all our customers in enterprise segments and even beyond are using it. So as we go towards more, I would say, telco use cases in that segment, what I see is that PTP time synchronization becomes a really important aspect for it, right? So for telecommunication use case, edge data center use case, because the customer wants to do the open RAN, like we saw a session yesterday from Meta also where they were talking about open RAN technologies, where you have CUs and DUs running in the virtual NFV appliances. For those use cases, having the PTP or enterprise data center providing those capabilities is very crucial, right? So in those edge data centers, if you have the capabilities of enabling Sonic, PTP is a must-have. So that's what we are focused on. And then, of course, there are multiple use cases in terms of federal and finance trading where PTP becomes more and more critical. So as part of the next phase in this particular session, what we are going to focus on how we enable PTP for the data center telco use cases, and then go beyond, as Saurabh said, into the front-end fabric, the back-end fabric, the AI/ML fabric in the future. Thanks. I'll hand it to Bhaskar.
Thanks, Sandeep. So we went over why open networking system and why Sonic and what are the use cases that Sonic supports today and what it is going to support in the future. And as part of telecom solution, PTP is required, right? I don't have to introduce PTP to you all, but without PTP, there will be people will be experiencing dropped calls, less bandwidth. All those issues will occur in the service provider network. So it is very, very important not only to have PTP, but support at a very high precision in terms of nanoseconds, right? So this is one 5G deployment diagram where the PTP switch is acting like a boundary clock and supporting the remote units to synchronize the clock with the grandmaster, again at a very, very high precision. We probably are familiar with a transparent clock, TC, which is simple to implement, but that cannot provide the accuracy required in service provider networks. So the rest of the focus on this presentation is mostly on the boundary clock. If you take a system diagram, right, like of a Sonic switch, it looks at a high level like this. There will be a forwarding switch, typically from Broadcom, and there is a host CPU where you have a PTP stack and a servo and other modules will be running, other drivers, and there you need to have some additional hardware modules as well, such as oscillators and DPLL, etc. With all these so PTP is very hardware sensitive, and obviously software also need to support that high level precision. So all these hardware software entities play an important role to deliver that class C, which is like, in the order of 10 nanoseconds. So what I am showing here is basically a high-level diagram where the packets will come to the switch will convert the packet timestamps as required to K-time and all, and pass it on to the Linux infrastructure. And the Linux infrastructure where the PTP stack and servo are running will process those packets. And once the time is received, the servo will be keep checking, right, with the silicon, and it will adjust the frequency as required so that the free running clock, which is essentially the timestamper in the switch, does not deviate a lot from the grandmaster. That's what we are talking about, synchronizing the switch timestamper very closely in the order of nanoseconds with the grandmaster. Right? So the boundary clock plays two roles, right? One is it acts like a receiver to the grandmaster, and it acts like a transmitter to the ordinary clocks. Ordinary clocks being the remote units that we saw in the previous slide, the endpoints. And of course, when you have multiple hops in the network, each hop is acting like a BC. So, on the one side, it will be interacting with the grandmaster, and the other side, it will be acting like a transmitter to the other boundary clock switch. There are several standards to meet because when you are deploying this in a telecom network, 3GPP ITU standards need to be met, and there are several standards. I'm not going to go through each of those standards, but traditionally there is one set of standards that expect every switch need to be PTP compatible, meaning every switch has to be a BC. So that is called full time support, right? And the recent standards, what they are allowing is you can go through parts of the network that are not PTP aware, and that is called partial time support, PTS. And if you have a GPS and supported PTS, that is called APTS. So these are like three different variations of standards, and obviously the most important one, because of the legacy reasons, full-time support needs to be supported, and wherever possible, that 75.2 that we are showing here is the partial time support. And we are happy to share that we can support all these standards related to PTP and also Synchronization, because Synchronization plays a key role in providing frequency synchronization at layer 1. Right, so we can support those standards as well. So to summarize, as you saw, SONiC is becoming very important in a lot of segments, and it is getting deployed in telecom networks. And without PTP, it cannot support various use cases in telecom networks. So that's where we are adding this support. And as you can see in the graphic that we are showing, the two-way time error is Class C compatible. So Class C is very hard to achieve, and that is, 5G networks expect a Class C type of performance, and we are happy to share that we can support Class C as well. And with that, I will hand it over to Ullas. So Ahmad, we will take questions after his presentation. Okay, yeah, thank you.